Hola. Muy bien, vamos a dar inicio al coloquio extraordinario que nos va a presentar el doctor Luca Celardo, un buen conocido de muchos de nosotros, amigo, que nos va él es un experto en largo alcance, cooperatividad, este, bueno, a ver, por favor, Luca.
Así. Bueno, la charla va a estar en inglés, si no puede decir demasiadas groserías, porque sé hablar español de la calle, decimos. No, no, no científico también. Okay, so okay, before starting, I know many of you, I know Francois, of course, so I don't need to ask you what is your field. Maybe for the people I don't know, it would be good to know what is your field, just to cosmology. So perfect. No match at all, but it's good, it's good. Optics, okay, that's good. Material science. Say, Louise, I know. And you over there? Okay, many things, good. Then there is overlap for sure. No problem with it. And you? Material science. Atomic physics, okay. And you know, I know because I've been used. Interstellar medium, okay. And you? Tangent stars was perfect then. Okay. Now, sorry for this. It's always good to know what the audience know. So I will talk about quantum transport and the new features that arises in quantum transport. And let's say the general question of the field is how energy and information propagate through complex disordered system. And what are the intrinsic transport properties, and how these intrinsic transport properties are modified when we have external noise. These are the general questions that whoever of you works in quantum transport knows that are relevant. And these questions are relevant, of course, for instance, to drive the supposedly coming next quantum revolution, right? Meaning that a device is able to work at room temperature. Apparently, AI already came way before the quantum revolution, artificial intelligence, and which will be a great revolution, of course. Fortunately or unfortunately, I don't know, in our lives, okay? But anyway, these questions are essential to build, for instance, a quantum device that can work at room temperature. And my talk will be divided in two parts. The first part will be about intrinsic properties, so no external environment, in long-range interacting systems. Okay, actually, interacting is not really precise. Long-range hopping system. Okay, so it will be about quantum simple particle transport. And the second part will be transport properties close to criticality, but in presence of environmental noise. Okay, so there will be these two parts that will cover, let's say, the context that I just outlined. So let's start with the first part. So in the first part, no environment. It's all quantum mechanics, okay? And we will talk about the interplay of Anderson localization and long range. So I guess, I'm not sure how many of you know. Who doesn't know Anderson localization? Okay. No. Okay, okay, good. I have a slide. I know the others are even more expert than me in this field, but no, what is undersoil localization is very more or less simple to say, is that if you have disorder, let's say that you have an excitation is moving, but there is some sort of disorder then due to interference, this excitation will not spread diffusively, for instance, like you would expect if there is some disorder, typically things moves diffusively, but it will stop spreading. And this is called localization. It's an interference effect. It's not only quantum mechanics, it's a wave effect, okay? It's due to interference. And it was a beacon. This effect was discovered by Anderson, and it was a beacon to understand what happens in transport in disordered system. How, Thomas? I just started with Anderson localization, so you didn't miss anything. And this is an experiment which has been done in Florence by Roati, the Roati group. And you see, here, these are cold atomic clouds. And this is for zero disorder. And here you increase the disorder. This is time. You see that for zero disorder, the cloud will expand, right? There is transport, right? But then as you increase the disorder, there is no expansion of the cloud. This is an example of Anderson localization. And the eigenmodes of the system, when they are localized, are exponentially localized. And these are the exponentially localized eigenfunction that they found experimentally. So the scaling theory of localization says that in 1D and 2D, wave function are always localized. So in principle, transport is suppressed exponentially with the system size. While in 3D, there is a very interesting effect still discovered by Anderson. There is something called mobility edge. What does it mean? It's a critical disorder, for instance, above which things are localized and below which are delocalized. More than critical disorder, mobility edge often refers to a critical energy below which the states are localized and above which they are extended, or vice versa. So meaning that you can behave like a metal when your eigenfunctions are delocalized, or like an insulator. So that's why these transitions are called metal-insulator transition, because if your eigenmodes are localized, then the excitation doesn't go anywhere. It doesn't move, okay? So disorder typically blocks the excitation spreading, blocks transport, and there is a mobility edge, a phase transition in 3D, etc. But this model, this framework, which was very important for the last 50 years, it was really a beacon to understand what happens in a disordered system, is valid under some assumption. The first one assumption, okay, Anderson considered a lattice, so the particle can jump on a lattice, let's say, but most importantly, the jumps are nearest neighbor, and the system is closed, it cannot lose things. The excitation cannot escape the system. So, but if we start to relax one of these assumptions, then we are not sure what happens, right? And for instance, the assumption that we relax today with you is that the hopping is not only nearest neighbor, it will be long range. There are many physical systems when there is long range, for instance, in cold atomic clouds and in photosynthetic systems. They are both in different regimes, because here in this case, the wavelength is larger than the system. Here, the wavelength is much less than the system, because this is millimeter size. This is the cloud of my collaborator, Ben Kaiser, in Nice. But in both cases, they are described by the same Hamiltonian, because you have dipoles interacting with the electromagnetic field, which generates a long-range interaction, long-range hopping. In cavity physics, also, you have long-range hopping mediated by the cavity mode, because say that you have a linear chain, the excitation is here, it can go to the cavity and then come back to any sides. And this generates an effectively long-range hole-to-hole, actually, hopping between the sides. And in ion traps, long range can be engineered and tuned. They can generate one of R and D alpha interaction hopping, where alpha can be tuned experimentally from 0 to 3. So you go in 1D, you go from very long range, 0, all to all. Basically, you can reach any site with the same intensity, to alpha 3, which is almost short range, okay? Now, what Anderson and Levitov already discussed, what they expect that long-range hopping how they expect that it would affect localization, okay? So if we have long range, what they said is that localization should be broken. Why? Because, you know, you have your energy, say that you have a chain of sites with different energies. Then you can reach any site far away. This energy fluctuates because there is disorder, but in space, not in time. I'm talking about space fluctuation. But if I have a long range, sooner or later, I will find a site which is at resonance. And so I can go very, very far. Okay. So the general expectation is that the long range should destroy localization and favoring transport then. But this is not exactly what happens because it depends on the kind of long range. And this is, let's say, a recent realization that people understood, meaning that if you have correlated long range, this is an example of correlated long range. This site is coupled to all the others, but with the same intensity. So correlated long range meaning that the hopping to sites which are at the same distance are the same, the hopping amplitude. Uncorrelated long range is like people, here we have one of the sanctuary of random matrix theory. This is the example of random matrix theory. Long range is random, is uncorrelated. So it doesn't matter the distance, these gamma are random numbers, right? In this case, if for uncorrelated long range, then it's true what Anderson and Levitt thought. Long range does destroy localization. We have, okay, you overcome localization, but for correlated long range, then that is what I will focus today, which is very physical. I consider when you have 1/r the alpha interaction, which is what physically you have, everything at the same distance have the same hopping, okay? So I'm not talking something weird correlating long range. It's something that you have a microscopic long range interaction is correlated typically, okay? You have to make an effort to make it uncorrelated. So in this case, things behaves very differently, and that's what I'm talking about, okay? In this case, I will show you that you can have localization and you can have other interesting effect. So let me say some general features of correlating long range, spectral properties. So first of all, they're typically characterized by gapped ground state. So contrary to uncorrelated long range, the spectrum is not uniform. You can have many gaps. Of course, you have a gap between the ground state and the first excited state, but you also can have other gaps. And this gap can be described by the same way people describe the BCS gap. Okay, it's the same mathematics of the Cooper gap. Okay. In the gap regime, the ground state is extended and robust to disorder. This is no surprise because if there is a gap, the ground state, until the disorder matches the gap, the ground state will remain delocalized. Okay. On the other side, the excited states are not gapped and so much more affected by disorder. Okay. So in correlated long range, the effect of disorder is non-uniform on the states of the system. Some states are robust and remain delocalized. Other states will be affected. Okay. Since the excited states constitute the vast majority of the states, and they have an hybrid nature. So I said that the ground state is gapped and remain delocalized. The hybrid states are not gapped. They are affected by disorder, but they localize, but in a particular way, meaning that instead of having wave function which are exponentially localized, we have hybrid wave function with an exponential peak and then tails, which can be power law or a plateau if the interaction range is all to all. Okay, these are called hybrid localized states. But since these excited states are the vast majority of the states, they determine the transport properties. And that's what I will talk about. What are the transport properties when you have correlated long range? Okay. So I have this, I forgot. Okay. What is the physical system that we consider? So we have a chain of sites. You see, every site have a different energy. That's why they're not on the same line. In the Y, you can imagine there is the energy. Then there is a nearest neighbor hopping, and there is a long range hopping. So every site is connected to all the others with the same intensity. Let's take for convenience now all to all, but then I will generalize to 1/r the alpha. Okay. And then we have pumping on the first site and drain on the last site, and then we study current. Okay. We also study the spreading. We start the excitation in the middle, and we see how the wave packet spreads. And we study the stationary variance of the wave packet. They both give the same results. Okay, we'll focus on the current now. This system can be mapped into a cavity physics system when the cavity is like an external site that couples to all the others and generates all-to-all long range. We did the mapping in the paper. If you're interested, you can see. is pretty accurate, the mapping, I would say. Now, mathematically, the Hamiltonian, it has an H naught plus V, where V is this all-to-all long-range hopping, and H naught is the Anderson model, which is you have disordered site energy, where the energy here can go from minus W/2 and plus W/2 randomly. So this W represents the strength of the disorder. The larger, the more disorder are the sites. And then you have a nearest neighbor hopping, okay? On the top of it, you have this long range. This is the bare Hamiltonian. Now we study the current and we are the right. Before coming to that, let me tell you what are the characteristics of the Hamiltonian system, and then we will do a master equation and I will show you. So in absence of long range, then this is just the 1D Anderson model. We know the eigenfunctions are localized exponentially. The maximum localization length is proportional to omega over W squared, okay? And this implies, since we have exponential localization, that the transport, the transmission through the chain is exponentially expressed in the number of sites, okay? That's a clear signature of localization also. As you increase the size, you have exponential suppression of the transmission. If we have all-to-all long-range hopping, then what you have is that you create a gap. The ground state now is gapped. This is the amount of the gap proportionally to the number of sites. And you need a disorder. You can compute the disorder that you need to destroy this gap in the system. This is the formula, is gamma n log n. This is the BCS formula, okay? It's the same of the BCS gap. Okay, is the Cooper, if you look at the article of Cooper, is the same gap because it's the same Hamiltonian. The Cooper Hamiltonian is the same of a long-range Hamiltonian, but is written in the momentum base. Okay, so given that now we come to the important question of Luis, how we compute the current, right? So one thing you can do is not the smartest thing, that's why we did another two things, is to use a density, a master equation, when you have an operator that pumps and an operator that drains from the last site, an operator that pumps the first site. And then the current would be just this, is the drain times the probability to be on the last site. But this is equivalent to this formula, where tau is the average transfer time. This is an equivalence that we demonstrated mathematically in the paper. We call it the tau method, but you can call it whatever you want. The point is that with this method, in which basically how you compute the transfer time, you use a non-Hermitian Hamiltonian when there is only the drain. You start from the first site, and you compute the average time the excitation needs to go out. Once you have this average time that you can compute just by diagonalizing the Hamiltonian, the non-Hermitian Hamiltonian, then you plug it here, and we proved mathematically these are the same thing. So in this way, we were able not to use the master equation, which is numerically very expensive, and we were able to simulate 10 of the 4 sites and more, okay? So this was a nice methodological results, let's say. Now, that's the main result I will show you, and this is the end of the first part. After this, I comment on this result. So let's look at this figure now. That's all what we care, right? Here on the Y is the current, and on the X is the strength of the disorder. Now, the blue curve is what would be a chain without a cavity, so without all-to-all open. As you can see, these are 10,000 sites. As you can see, the current, I mean, this is a finite size effect, and then it goes down very steeply because this is Anderson localization, okay? So this is the blue curve. The red, look at the red, forget about the orange. Look at the black dots, is what happens when you place this chain into a cavity. Okay, and so you have all-to-all coupling. You see, at first you behave in the same way as the Anderson chain, but then you go down much slower with a power law, not exponentially. But then there is a turning point at the critical value of disorder we call W1, at which the current goes up instead of going down. So we have a disorder enhanced transport regime. And then there is another critical point, W2, at which the current becomes independent of disorder for order of magnitude. And then when the disorder closes the gap, this is W gap, then the current goes down again. So here we are, all here is in the gapped regime. So that you need a gapped regime in order to see this effect. So as you can see, this is very different by the standard Anderson, let's say, or I mean, it's not fault of Anderson, but let's say, but the standard paradigm of what disordered system can do to transport, okay? Here, disorder we see with long range can enhance transport and can make transport independent of disorder. Now, the difficult question now is to answer why there are these regimes, okay? On one side, you know, physically you can say, okay, there is a cavity. I start with the first site, and if there is all-to-all coupling, only the extended state is coupled to the cavity. So if I start with the first site, I have 1/n probability to be in the extended state. So I have a very small probability to be in the cavity. Disorder enhances the possibility to go in the cavity. Once I'm in the cavity, from the cavity, I can reach the last site more easily. And so cavity can enhance the transport, okay? This is the naive, let's say, the first thoughts you can think of why there is this enhancement. Of course, this doesn't explain why this enhancement starts here and why there is a disorder-independent regime. And indeed, this idea that the cavity, that everything is determined by the presence of the cavity, I mean, the cavity is necessary, but doesn't explain what happens. What happens is a tricky interplay of the requirement of orthogonality, because you have an extended ground state that is untouched by disorder and is fully extended, and all the other states, they are affected by disorder, but they need to remain orthogonal to that state. And this interesting interplay, it makes, you see, now I show you, here I show you the shape of the eigenfunction of the excited states. So they are all the states but the ground state. You see, now for W1, we are here in the turning point. For W1, you have this black line that goes here. And the black line below is the Anderson model wave function. You see, it's the same of the Anderson model, but then at the tail, they go higher, right? And then these tails increase. As you go from W1 to W2, it increases, okay? And then above W2, the tails don't move at all. Let's say the shape of the eigenfunction of the excited states determines all this transport regime. Indeed, this orange curve, we have obtained it by using analytically, by using perturbation theory, just disregarding all the coupling between the excited states and the ground state mediated by disorder. So let's say it's enough that you impose an orthogonality condition on this, that disorder is there. It has to arrange with this orthogonality condition to understand this transport, okay? So the only role of the cavity here is to exist. It doesn't touch the system. It's like the hands of God, let's say, you know? It's a ghost effect. The only fact that this exists is enough to determine all this, okay? And I tried yesterday, every time I look at this, I have doubts. No, I have doubts, so I asked my student, can you plot me the probability to be in the cavity throughout this W regime? And she sent me the results this morning, and it's constant. The probability to be in the cavity is 1/n, it's constant. It doesn't feel any of these regimes, okay? This to confirm that this is really a ghost effect. It's not a direct effect of the cavity, but okay. Let's go on. How we determine W1 and W2. W1 is when the exponential probability of the Anderson model reaches the tail, the plateau 1/n, and W2 is when the exponential probability on the closest sites reach 1/n, okay? So you can see that the W2 is when the transport starts to be stable, and maybe you can understand why, because here is the maximally localized situation, and then disorder cannot change anything else, right? You have a plateau, you have a localized states, and it stays put. The plateau doesn't move, okay? Analytically, again, mathematically, you can understand all this. We can prove this with perturbation theory that the tail does not depend on W. Physically, it's harder to understand because it's a tricky interplay. Okay. So we have shown that the current and both the spreading, if we compute the spreading, they have this disorder-enhanced and disorder-independent transport regime. One thing to notice is that here at the beginning, the transport is identical between the Anderson model and the model with long range, a very strong long range. And the fact that transport is identical is not trivial. And this is due to another interesting effect that exists in correlated long range system, which is called cooperative shielding. So why the transport? You have a chain without long hopping, and then you have a chain with long range hopping, and they give the same transport. This is non-trivial, and this is another interesting effect of correlated long range systems. And then these I already said. And this is the final slides of the first part of the talk. You see here we change the range of the interaction. Alpha 0 is the figure I showed you now, the current versus disorder. When you have disorder enhanced and disorder independent, then you go down. But then if I take 1 over r at the alpha hopping, I still have the same general features. I lose the disorder independent regime, but I still have the disorder enhanced regime, even for alpha 3. And then for alpha 10, you just have the typical chain, short range, near neighbors chain behavior. So this disorder enhanced regime is really a general feature of long range hopping disorder system. These are preliminary results. We didn't publish this extension to finite interaction range, but I presented to you and we will be publishing soon. Okay, so the first part of the talk ends with this general message that long range has this very interesting and novel transport regime, which has disorder enhanced, disorder independent transport. And now I start the second part of the talk, in which we will analyze the effect of external noise on transport at criticality. So the idea actually of this work that we published recently was started here in Cuernavaca during a workshop where I was talking with Orazio Pastaschi, and he told me, actually we both had a look at these works by Kaufman and Gabor Vattai. I don't know, maybe many of you know who is Kaufman. He's a very, let's say, influential figure in philosophy and complex systems. He's a biologist, but he's also a philosopher and so on. And Gabor Vattai is a physicist. They worked together and they published some papers about quantum biology and on the edge of quantum chaos. And their idea was that biological systems are work at a phase transition, at the metal insulator transition. So that the parameters in which biological molecules are tuned by nature make this biological molecule to be close to a metal insulator transition. And this is a good place where to be. Okay, that was their claim. And they did some work. I have to say that I like more the claim than their results to prove the claim. I don't want to offend Gabor Vattai, with whom we discussed and so on, but that's what we discussed with Orazio. Okay, we liked a lot their idea, no, but we were not convinced by the results they had, and so we studied the same system they studied, which is the Harper model. Okay, so the Harper model is a 1D model in which the energy are not the same, but they don't fluctuate randomly. They fluctuate in a deterministic way, but the phase is given by a rational number. For instance, we use many rational numbers, but typically if you use the golden mean, which is the most irrational numbers, is good. And the peculiarity of this model is that you have a metal insulator transition in 1D. Because we have a metal insulator transition in 3D, but 3D is very complicated to study numerically. So we studied a model which has a metal insulator transition in 1D. What does it mean, a metal insulator transition? It means that WC is the strength of the potential. For W below 2J, where J is omega, is the hopping, which I'm sorry, I called it omega before, but now it's J. So for W below 2J, all states are extended. For W above 2J, all states are localized. And for W at 2J, we have precisely this phase transition, a metal insulator transition. So we have the border between localized and delocalized states. So what we did with this model, we studied the current, but again with a master equation, but now we put noise. How we put noise? We use the Haken-Strobel model. This is a typical model for excitonic transport in biological system. So we simply allow the energy in each side to fluctuate in an uncorrelated way in space and time. It is a white noise, okay? And the intensity of this fluctuation is gamma phi. It's called the phasing strength. And here's the master equation you get. And it's a kind of infinite temperature model, because this master equation has a stationary state in which all the sites are equally populated. So it's a diagonal density matrix, the stationary state. So it's infinite temperature density matrix. Okay. Okay, we used a quantum drift model, it's kind of quantum jump model to do the dynamics, because again, density matrix are complicated, but this doesn't matter now. What we compute is the diffusion coefficient. What does it mean? We place the excitation in the middle of the chain, we let it expand, and we compute how the second moment behaves. If it is linear, then we divide by 2t and we get the diffusion coefficient. Okay? Now I show you what happens in this Harper model without the phasing. Now, what is the dynamics without the phasing? If we don't have the phasing, here I plot the spreading of the wave packet versus time. The green line is in the metallic regime. You see, you have a ballistic spreading, then you have some transient, and then again a ballistic spreading. Okay, these dashed line are our analytical estimates, but it doesn't matter. No, the message I want to give you is that this is ballistic. Okay, for W larger than 2J, so above the metal-insulator transition, you spread at first ballistically, and then you localize. Right? At the metal-insulator transition, the spreading is diffusive. Okay. I mean, actually, there are details. The second moment is diffusive, like there are deviations at very large n. I mean, but let's say it's diffusive, like the second moment. And also, it's quite Gaussian, the whole spreading, okay? There are some deviation in detail. Of course, we computed analytically what is the diffusion coefficient. It is given by this mean free time times the initial velocity. We compute this the mean free time, etc. Right? The mean free time is the time at which you start to scatter in your system. Okay. This will be an important quantity. So this is the situation: the metal regime ballistic, localized, and then diffusive. Now, what happens if we add the phasing? The symbols now, if you add the phasing. So the first thing that happens when you add the phasing is that everything becomes diffusive. Okay, everything. So the localized system diffuse, doesn't localize anymore. The ballistic does not spread ballistically, but diffusively. So with less velocity. And at the metal-insulator transition, we had a diffusive behavior. We still have a diffusive behavior, but notice that the diffusion coefficient remains the same. Now, you might say, okay, but this is because gamma phi is very small, right? So let's see, let's compute the diffusion coefficient for different noise strength. So in the metallic regime, as you increase the noise strength, the diffusion coefficient goes down. These are the two different parameters from the metallic regime. In the localized regime, the diffusion coefficient goes up because, let's say, transport here was very bad, so the phasing helps up to a certain point, and then it goes down. For very large dephasing, this is the quantum Zeno regime, the diffusion coefficient goes down in a universal way, and that's it. Okay. As you can see, interestingly, at the metal-insulator transition, the diffusion coefficient is independent of the external perturbation in a very wide range of noise. Okay, not only for small noise. Okay, and here's another figure that shows the same effect. Here is the diffusion coefficient versus for different disorders, and you see they all intersect at the metal-insulator transition. Okay, so you have this interesting effect that transport is very stable at the metal-insulator transition in this model, which means it responds to its own law independently of the amount of noise you put in the system up to a critical noise. And this critical noise is where the dephasing time is the same of the mean free time. So basically, when the dephasing time is faster than the scattering time, then you affect your system. But as soon as it's lower, your system diffuse with the same diffusion coefficient as if noise would not be present. Okay. Of course, this stability is very intriguing, but we wanted to understand what was the origin of this stability. It was because the system is diffusive, or it was because there was a metal-insulator transition. It was the phase transition that made, we know the phase transition has very intriguing properties, right? We have universality, scaling, free parameters, right? Self-similarity, okay? So what was the origin of these disorder-independent, diffusion coefficient of this does not depend on noise. And then to answer this question, we study other two models. The Fibonacci chain, where there is no metal-insulator transition, but there is a diffusive regime, and the PBRM model, of which some of you are extremely expert. As you know, in the PBRM model, we have a metal-insulator transition, but we also have a diffusive regime, which occurs in a broader range of parameters around the metal-insulator transition. Okay, let me briefly present these two models. So the Fibonacci model is just a linear chain in which this disorder potential is not disorder, but is given by the Fibonacci word sequence. So the first is not modified, the second is not modified, then you have W, etc., right? You follow the Fibonacci sequence. In this model, the spreading of the wave packet is start in the middle, is super diffusive for a certain value of W, subdiffusive for others, and is diffusive at this value of W. You see, this is super diffusive, subdiffusive, and you have diffusive. And if we now add the disorder noise to this system, again, we notice that the diffusion coefficient is independent of noise when it's diffusive, when the intrinsic dynamics is diffusive. So even without a metal-insulator transition, when intrinsic dynamics is diffusive, we found, we found with this independence of the diffusion coefficient from noise. And the same occurs in the band random matrix model, where you know is a long-range hopping model, where the range of the hopping is mu, B is the kind of the size of the first sites interaction. And we know that here there is an infinity of metal-insulator transition, and they occur all at mu equal 1, but for different value of B of different universality class. But in this model, you have diffusive spreading of the excitation in the second moment for mu between 1/2 and 3/2. So in a large range around the metal-insulator transition. And in all these cases, when you have diffusion, second moment is diffusive, we found the same independence of the diffusion coefficient from noise. Now, we computed analytically the dependence of the diffusion coefficient on noise, and we found this was based on a model, because this dephasing can be seen as a local measurement, which occurs with Poissonian times of your particle in position, a local position measurement, okay? Doing this, we were able to derive the diffusion coefficient as a function of noise. So tau phi is the dephasing time, tau w is the scattering time. So you see, if you divide by d0, which is the intrinsic diffusion of your system, you have a formula that does not depend on the details of the system. Depends only on the ratio of the phasing time of the scattering time. And all the models, when they're diffusive, they fall on this universal curve. You see, this is the squares are the Harper model, the Fibonacci model are the triangles. Then we have the PBRM model for in the metallic regime, 0 age, at the metal-insulator transition, and in the localized regime. And they all have the same behavior. And you can prove that the correction to the initial value of the diffusion are quadratic and not linear. So they're not really independent, but it's a very small correction. Okay. Now, if one question, so now the comments I want to make to this result are the following. So whenever, so the result is the following, that whenever you have intrinsic diffusion, then your system, quantum intrinsic diffusion, because these are quantum systems, your system does not respond to its own law. It is not affected by the way it diffuses by external noise, okay? Up to a very large value of noise, okay? This effect, actually, it responds, if we make a model, you know, typically, here we have two processes which generates diffusion, right? You have the intrinsic dynamics, and then you have external perturbation. You might think the diffusion coefficient would be the sum of these two diffusion effect processes, right? But it's not. Or if we take, for instance, two independent Poissonian processes, that's what we did in the paper to understand these effects, then we would have a linear correction to the diffusion coefficient, not a quadratic correction. Okay, so now the question we want to understand now, and we are working on this, is whether this is a quantum effect or not. So the question is that a classical system where you superimpose two sources of diffusion would be independent of diffusion like a quantum system. Is this a quantum effect or a classical effect? Okay. So I would like to end that we were inspired by this work, by the idea of Gabor Matai and Kaufman, that criticality might be a good place to be for biological system. And of course, for biological system, it's critical to respond that they need to function according to their own law and not to the independent of the external perturbation. Okay, so this is a very important feature of biology, right? We need to be able to perform whatever we need to do, independent of what is the temperature outside, or if there is windy or not windy, okay, etc. Right? So these let's say independence of the or external perturbation, it could be a very important feature in biological system. Now, the idea that they had that metal insulator transition is important, or the way it was important, maybe it was not consistent with our results. But still, I would say the fact that we find these, let's say, strong independence from external perturbation, whenever the intrinsic dynamics is diffusive, you know, diffusive, you have a coherent dynamics. You can, I know, I'm sure we can discuss with many of you about this. To have an intrinsic coherent deterministic dynamics, which is diffusive, and diffusion means that the system behaves like if you toss a coin, right? It's not a trivial thing. Diffusion is a critical regime because it's self-similar, okay? So in a sense, diffusion is a signature of criticality, okay? Even if it's not directly connected with the metal, with a phase transition, okay? But still has many features of criticality. So the general claim that I would say that Kaufman maybe had a good idea. The criticality in general can be good for biological system and for transport. And the way we specified this importance, I would say, is that by criticality, maybe we mean intrinsic diffusion, quantum diffusion, can give stability to systems in general, to quantum system with respect to external perturbation. And this maybe is the poison real of which Kaufman thinks about. That's why we're studying realistic biological system to see whether they respond to temperature variation and to external perturbation, and whether they, in natural disorder they have, gives them the ability to be diffusive. Okay, and that's what we are studying. And that's okay. I'm done. But before finishing, I would like to make an announcement that on quantum biology, we just won a European project that aims to build a sunlight power laser, so a laser that works with the sun. And so I invite you all to follow us on this website and to follow on Instagram and etc. Because this is let's say, is connected with biological system, because we want to build this laser using photosynthetic antenna systems. And this is the final announcement I want to make. Okay.
Questions? Rafa?
Of course.
Exactly. Here, alpha equals 3 is the boundary. Is the system three-dimensional?
One-dimensional, sorry. Exactly. So the point is that yes, this is as you know, the critical dimension would be alpha 1, right? Exactly. You would expect. But as you know, it's also between 1 and 3. It's a weird statistics. For instance, in statistical mechanics, there are weird effects at alpha 2. So it's not fully short range until alpha 3, I would say, no? So there is long range as far as extensivity, right? Alpha 1 is what determines the threshold, absolutely. But for instance, I make you a stupid example. The gap between the ground state and the first excited state behaves differently below alpha 1, between 1 and 3, and then above 3, for instance. So there are features that this is a region in which you have weird transition from long range to short range, and is not totally short range up to 3. Okay. Okay. Yes.
No, it's not.
Okay. Okay. Yes.
What's your attitude towards the fact that we need to fine-tune the value?
Which fine tune you mean? Yes. That's a good point. So let's come to this point. So you see, in the Harper model, it's true. Criticality, which means diffusive regime, occurs only at the MIT, right? But for instance, in the PBRM model, right, a criticality, diffusive regime occurs in a wider range, mu between 1/2 and 3/2. In finite size biological system, which are neither 1D, neither 3D, for instance, you have nanotubes, right? That's what we are studying. So in a finite system, you can have a range of disorder, which actually, I can tell you, from the first analysis we did, in this range of natural disorder, which goes from 500 centimeters -1 to 2000 centimeters -1, for instance, no? And then the motion is diffusive-like in this photosynthetic system, for instance. Exactly. Then another question that I would like to discuss with you, since you are the one, is the connection between chaos and diffusive intrinsic behavior, which you know, which maybe we'll talk later, but I just anticipated this issue.
More questions? Yes.
Hoffman, okay. Yeah.
Where which kind of disorder?
Yes.
So I was thinking it was quite.
Yeah.
Can you say a bit more about this? If I understood so.
Yeah. So, okay. So look, this is our statement. Kaufman just made a statement that he says you need to be a criticality. So I tell you, look, in plain words, why Kaufman and Gabor claimed that criticality was good. Because localized state stays coherent for a long time. So you see, a criticality, what you have. Above criticality, you have localization. Coherences last very long in localized states because they are not disturbed by noise, but transport is bad, okay? In the extended phase, coherences get destroyed very fast, but transport is good, okay? So they say at the metal-into-laser transition is the best because you still have good transport, it's a kind of good transport, and coherences are not destroyed so fast like in the metallic. So it was a very qualitative statement, okay? That's all they said. But nevertheless, we like the idea. The criticality was good, okay? And we wanted to study the Harper model. And then what we found is in a sense, nothing to do with what they found, but if not that we were inspired by what they said, okay? And our claim now is grounded on analytics and numerics and so on, is that when you have intrinsic quantum diffusion, you are extremely stable to external perturbation, okay? And this is the kind of advantages that you have at criticality if we extend the notion of criticality not only to the presence of this transition, but to the presence of the diffusive regime. Okay, so we can say in a certain sense that to be diffusive in a sense is to be critical, because diffusive is a very special the regime to be in a sense. Okay, that's all.
More questions? I have a question too. I see that you present several results making disorder in the sites, but not too much in the hoppings.
Yes.
This result is the same, or?
Well, you know that there is in Anderson model there is a small difference. No, if you make disorder in the hopping with respect to the sites, no, there is a delocalized band in the center, the localized states in the center, but the general feature should be changed so much, I would say. Even if you have to be careful, right? There are some differences, but the general features are not It shouldn't be different. And as far as you are interested, these, since you can measure in your lab eigenfunctions, these hybrid states and the behavior of these hybrid states as a function of disorder would be something that one could use to prove this disorder enhanced and disorder independent regime, for instance. And this is static, right? Doesn't require current or dynamic. I mean, we can discuss this better later.
Yes, just coming to this this part, which will be a small size in which you can see this stuff, because you know, to make a very a big experiment, a system with many sites will be very hard.
Yeah. No, look, I don't. I mean, the size. I mean, the problem of the size could be overcome because this W, you know, it depends on the size. So if you have small so what you need is a strong coupling so that you have a gap, first of all. Then you need this W1, W2 to be below the gap. And then you should be able to observe, you know, these effects. One occurs when the localization hits 1/n, and the other when localization at the edges hits 1/n, and this is when the localization on the nearby sites reach 1/n. So probably, I mean, larger sites would help to have a clear signature of the, because, you know, you have to find the shape of the eigenfunction. If you have 6 sites, the shape, but probably something, I mean, larger would be better, but maybe something can be done also for small size, no?
Okay.
Maybe something can be seen. In transport, for sure, it would be, it could be seen, no?
Okay.
Maybe also the eigenfunction. We need to think about it.
Okay. More questions? No? There are no questions, I guess, in the internet, or somebody? Okay. Okay, we thank again the Luca.
Thank you
for
for
excellent
this, yes.
presentation.
Thank you very much. Thank you.